Hey everyone, we're just going to take a look at doing a problem with forces, mass, and acceleration, Newton's second law, but this time looking at objects which would be sliding down an incline. And the only real new physics to the problem is figuring out how do we deal with this when we're not on a traditional horizontal surface or something accelerating horizontally or something accelerating in the vertical direction. Well, really, that's just a point of view on how you take a look at things. If we take a look at our free body diagram, okay, and think about how the ramp would be, working with the skier here, we realize that the force of gravity always still pulls straight down towards the center of the earth. The ramp can always only push, right, perpendicular to itself. So if we put some labels in here, this is our force of gravity. This is our normal force. And since we're going to have some friction, they tell us the coefficient of kinetic friction between the skis and the hill is 0.150. We know that we're going to have force of kinetic friction which would oppose the motion. All right, so we can just go ahead and label that as we always do, force of kinetic friction. Okay. Well, the question would be then, how do we, once we have our free body diagram, right, how do we go about and start resolving our vectors to come up with our system of equations? Well, here's what we can do. We can take our coordinate system and we can tilt it so that one of our directions, the x direction, is parallel to the ramp, right, and our y direction, our new y direction, is perpendicular to the ramp. So with this new parallel and perpendicular direction, we can have our forces line up with vectors we're interested in, and especially interested in the motion straight down the hill as being along one of our directions. That greatly simplifies the problem. So now we could take a look at setting up our t-chart and working with our components like we would normally do. Now this x direction, okay, sometimes books will call it the parallel direction. Okay, either is fine. I like to use x and y. The y direction is the perpendicular direction. And we're going to sum up our forces, right? So we're looking at our x components of our forces and our y components of our forces again. Well, you can take a look at the normal force, and that's just like it usually is. It's just directly upwards in that y direction away from the ramp. So I'm just going to label that here as the plus direction with no component parallel to the ramp or in our x direction. And the force of friction, like always, is going to be, okay, opposing the motion, and it's got to be parallel to the direction of motion, right? And so there's no y component or perpendicular component to that one. Now the force of gravity, right, does have a component both in this perpendicular and the parallel direction to the ramp. So what we do is we just resolve our vector triangle horizontally or along, not horizontally, but parallel to the ramp, all right, and also perpendicular to the ramp along our two axes that we're using. So with that, the only new little twist on things is to realize that this angle theta that they're telling us the hill is at is also going to be the angle that the y-axis, okay, now makes with its former direction. So if we tilt x away, if x is tilted away here by theta, right, then we know y is also going to get tilted away by this same angle theta. Take a look at what happens here when I tilt the coordinate system. See? Y tilts away by that same angle theta. So we can write now, with this reference to this angle theta, we can write our force components for gravity. In the x direction, right, this is going to be Fg opposite side. Sine of that angle theta, and that's in the forward direction, plus. And this component would be downward, okay, and that's going to be cosine, since it's the adjacent side of that vector triangle. So we can just write positive force of gravity sine theta and negative force of gravity cosine theta. That's the new little twist. And so now we've got our components. Once we've got that, now we just solve with the math equations that we're used to working with again. So the forces in the x direction are going to be force of gravity sine theta minus the force of friction equals the mass times the acceleration of the skier down the direction of the hill. And in our new y, or perpendicular direction of the ramp, we've got the normal force upward, portion of gravity down into the ramp, and of course there's no motion in this direction perpendicular to the ramp. He's not leaving the surface, not going into the surface, so there's no change in velocity for the skier perpendicular to the ramp. That gives us our system of equations. So we're interested in solving in part A here for the acceleration. So if we do that, okay, I'll do it in one step. The acceleration divided by m, right, is going to be force of gravity sine theta minus the force of friction, all divided by m. All right. Now, from the y equation, like usual, we see that our normal force here now is going to be force of gravity, but it's cosine the angle theta. I'm going to substitute in here pretty quick. So remember, this allows us to rewrite this equation using what we know, right? Force of gravity is mg. This can be mg sine theta minus, remembering that force of friction is mu times the normal force. Now I'm going to write in for the normal force here. This is also, right, mg cosine theta. So I'm going to substitute this term in directly for the normal force in our equation for the force of friction here. Okay, so right here to right here. And this is all again divided by m. Well, if you notice, it's nice to keep everything symbols for a while because something interesting happens. Notice that down the ramp, the mass cancels out of these terms. And we find out something interesting, and we might actually expect this, that the acceleration is only due to a portion of gravity. It's independent of the mass. Plugging in the numbers given in the problem, okay, we'd have our 9.8 sine of 30 minus 0.150 cosine 30. And if you solve for the acceleration, we'll get 3.62 meters per second squared. So again, that was just the substitution and the solving that we're used to with the two equations, right? And the next two questions were how fast would they be going after 10 seconds if starting from rest, and how far down the hill after 10 seconds. So we just remember our equations of motion for speed after a certain time. If the initial velocity, right, is 0, it's just the acceleration times the time. So we could take 3.62 meters per second squared times 10 seconds, which would give us a velocity of 36.2 meters per second down the hill. Pretty fast. And the displacement in the direction down the hill if we start from rest is just given by the familiar 1/2 AT squared equation. And that will give you 181 meters down the ramp, or down the hill. That's a long hill. So anyway, just to recap real quick, all we did is tilt our coordinate system, draw our FBD like we normally did. We resolved gravity into two components, right? And any other vector we would have here, we would do the same thing. Resolve it in our new x and y directions. Set up our t-chart, and then solve our system of equations just like we've been doing to come up with our answers. And that's it.